Hey, hi everyone. Welcome to another Origin seminar. Today we are very happy to have us Rachel here. Rachel received their undergrad degree at MIT in physics and Earth, atmospheric, and planetary sciences. They went on to work as a mechanical engineer with the Harvard Cosmic Microwave Background Lab, where they supported the deployment of the BICEP-3 telescope, BICEP-3 telescope at the South Pole Station. Rachel completed their PhD at UC Santa Cruz in 2024 as part of the lab for adaptive optics, where they developed large format deformable mirror instrumentation and led high contrast imaging observations using CAC-NIR2. They are currently a research scientist with Eureka Scientific and are the PI of the two JWST programs that we will hear about today. And next fall, Rachel will be moving to Harvard Center for Astrophysics as a NASA SIGINT postdoc fellow. And Rachel, thanks.
Well, thank you. Wow, it's fun to be here. The last time I was here, I was a first-year grad student, so it's like very weird to hear my bio read back to me now. My research really focuses on thinking about new ways we can characterize exoplanets around the very nearest neighboring star systems. And I've been thinking a lot about characterizing giant planets that are more like the ones we found in our solar system. And today I'm going to share with you some of the results from two JWST programs, which I've been PIing, and talk about where I think some of this work could be heading next. Before I dive into my science, I also want to take a brief aside to talk about the naming of the telescope. JWST is named after the second NASA administrator, James Webb, who was in charge of NASA in the years after World War II and before the moon landing. And this period of time between 1961 and 68 was also the time of the Lavender Scare. And it's unclear about how much James Webb contributed to the firing of LGBTQ plus employees at NASA. And I'm sure while there's really interesting discussions in history to be evaluated here and nuances, and discussion about if it's appropriate to name telescopes after administrators and not an astronomer, and this particular administrator, I think it's fair to say that I, as an openly queer astronomer, probably could not have worked for NASA under Webb. And I'm not a NASA employee now, but I am entirely employed through NASA money. And next year I'll be taking a position as a NASA SIGINT postdoc fellow. And the astronomical journals have addressed this naming controversy by saying that you just have to say JWST. So you don't have to spell out the name of the telescope in your papers if you don't want to. And you'll probably hear me slip in and out of what I call the telescope, including my favorite abbreviation, JWST. And I once know someone who made it through a whole talk calling it the Jelescope-Wellescope Space Telescope. So I will not be doing that, but you can appreciate that history.
Sorry, Rachel, you turn on your video so that people like this.
Oh, yeah. Yeah.
Thank you.
Okay, but let's get back to some exoplanets on hand. So while we know about the existence of over 6,000 exoplanets, we don't actually know the majority of exoplanets that well. So let's imagine a scenario that you're on the Starship Enterprise when the crew pulls up to a planet and Kirk turns to Spock and told them to scan the planet, and Spock just replied, "The planet's orbital period is about 2 weeks." Or worse, he could say something like, "It appears that there's a minimum mass of 3 Jupiter masses. It might be bigger, though." And that's about where we're at in terms of understanding all of the planets that we've discovered. And while knowing some of these basic planetary properties has been amazing for identifying trends in the exoplanet populations and understanding how many exoplanets are really out there, we need more ways to characterize planets so our metaphorical Spocks can report back a more complete picture. So unlike most of the other techniques, employing the direct imaging method offers a way to study these worlds more comprehensively. In direct imaging, the light from the planet itself is measured directly. This is different from transit, radial velocity, stellar astrometry, microlensing, which all use light from the host star to then infer something about the presence of a planet. In direct imaging, you're more or less just snapping a photo of the planetary system. And most direct imaging work right now takes place using infrared wavelengths. So you can imagine it's sort of like having night vision goggles to look at the heat coming off the planets. And when planets form, they have a lot of heat from their formation, from all the mass coalescing. And JWST is one of the best pairs of night vision goggles that we've ever had in human history. The direct imaging technique works best for these reasons on young, massive planet systems. And it can also be of interest if you're looking for planets and like trying to study things at the solar system scales. For example, in direct imaging, if you are, for transit, if you are at 1 AU, it's incredibly rare that you're going to get a transit of a Earth-like planet. So it's a less than 1% chance. And RV and astrometry surveys can also take like a really, really long time, decades of baseline to get planets that are full orbits at the same scale of the solar system. In one image, we can also start to see this full system on like this baseline. So here on this picture that I'm showing is one of the most famous directly imaged planet systems. It's HR 8799, and you're seeing through multiple epochs the orbits of these planets get traced out, as well as getting the signatures from themselves, which let you go back and think about this sort of spectroscopy problems that you can evaluate with their atmospheres. Okay, so direct imaging is quite powerful, but and the technology challenges are tricky for many reasons. But ideally, we want to expand, and ideally, we want to expand what we can do with direct imaging. But what are we capable with now? Here's the ever famous exoplanet plot, which we see in every exoplanet talk. But I want to think about using this plot in a way that's slightly different. We often show this plot and talk about what planets we have observed, but what if we try to think about it more from what planets we could observe? So me and my collaborator, Logan Pierce, who is an alumni of here, pulled a bunch of references together from the literature for surveys a few years ago that report the planet occurrence rates for these wide orbit exoplanets beyond the snow line. And we sorted the occurrence rates into little colored boxes based on how rare they are. And the yellow regions of the plot indicate the type of planet is rare, and the purple and blue are most common. So there's two things I want to draw your attention to when we look at a plot like this. The first is that the prevalence rate of companions that direct imaging has already excelled at studying from these like ground-based surveys are young and hot brown dwarfs. And big gas giant companions that are orbiting outside 10 AU. These companions are actually super rare. Bowler 2018 finds their rate to be at less than 4%. But as you move into closer separations to this sort of 1 to 10 AU region and masses closer to that of Neptune, ice giants are appearing to be quite common in the demographics. The occurrence rate in this ice giant region that I've highlighted here in blue came from 2 microlensing surveys. The more recent paper quotes that the prevalence of ice giants could be as high as 1 to 2 ice giants per star. And now if that is true, and there really is an ice giant or 2 per star, ice giants could be some of the most common types of exoplanets in the galaxy. So that rate of 1 to 2 ice giants per star feels intense to me, at least. So let's stop and think about if there's a formation theory that could explain why there might be this pileup of ice giants and not gas giants. So we think an early step in giant planet formation, according to core accretion theories, is to collect together a bunch of solid rocky materials. And the time scales of this core material collecting could dictate the type of giant planet you get, a gas giant versus an ice giant. If the critical core mass threshold is hit before the gas from the disk blows away, is blown away by the star, a runaway accretion of hydrogen and helium gas could start, and you end up with a gas giant planet like Jupiter. But if the mass collects slowly or the core doesn't get enough material, the planet could miss its window of opportunity and to collect gases, and it may become something that looks more like an ice giant like Neptune. And I think we could imagine a universe where maybe more giant planets miss their window of opportunity to collect hydrogen and helium and end up as ice giants. And we could especially imagine this happening around like lower mass stars where you might not have as much mass in the disk. But then the question is, like, is this story of giant planet formation correct? Are there populations of ice giants and gas giants really as binary as I'm describing this story to be? And so finding and characterizing even a handful of ice giant exoplanets or exoplanets that are sort of on this border between the ice giant, gas giant divide could be really incredibly telling of testing these giant planet evolutionary theories. So the direct imaging method could provide this gateway we need to the sample of giant planets needed to study this problem, if we're able to reach these colder temperatures than any ground-based survey has yet provided. For reference, the smallest exoplanet that we've been able to directly image from the ground so far is about 2 or 3 Jupiter masses, and the coldest directly imaged free-floating brown dwarf is a little over 200 Kelvin. Our own Jupiter is, you get numbers between like 125 Kelvin, 150 Kelvin, and Neptune is about 70 Kelvin. And even when ice giant exoplanets are still really young, they're at temperatures of less than 400 Kelvin. So we're talking pretty cold here. I know different methods of observation have different definitions of cold, but I'm talking sort of in this range of certainly below 500 Kelvin, and really thinking more below 200. But JWST has incredible infrared sensitivity to cold objects. So how much could it really help? When I was a grad student, I was invited to a workshop happening at Space Telescope, where a bunch of researchers in the direct imaging community were coming together to chat about what might make interesting JWST proposals. And the majority of the discussion focused on imaging Gaia accelerating stars or stars in young moving groups. And Brendan Bowler suggested a wild idea to do a targeted direct imaging observation of a known radial velocity planet to measure a sub-Jupiter mass planet, so a planet smaller than Jupiter. There was one excellent candidate for something similar, for something that had more massive than Jupiter, and that candidate turned into Elizabeth Matthews' program on EPS in the AB. If you haven't seen this result, it's awesome. She made just this booming direct imaging detection of this super Jupiter planet that is so bright that it has little airy rings in the JWST MIRI images. But what about planets that are smaller? So I was surprised the idea was so dismissed, because I'd been thinking about this from a ground-based observing perspective. As part of my PhD work, I completed a high contrast imaging survey using KEK-NERC 2 of the Wolf 359 system. This is our 5th closest neighbor and is a relatively young M dwarf. And we were trying to confirm an RV candidate that looked a lot like one of these exo-Neptunes. And in the end, we couldn't get the sensitivity from the ground that we needed. And we just barely placed some sub-Jupiter mass limits. So surely there must be a JWST direct imaging strategy that could do something similar but reach those depths. So when I was trying to explore this idea, I made this plot and to try to explore the major advantages that you get when you're targeting systems that are right next to us. The proximity makes any potential companion appear at proportionally wider separation angles from their host star from our vantage point, and it boosts the apparent magnitude of the companion logarithmically. And so when I was sketching out this idea, I made a plot and this sort of like how close is close enough. And this is a plot using the Linder 2019 models of the planet's apparent 4-micron magnitude as you view targets from further away. And the dotted black lines represent the sensitivity of different instruments. The top ones are for Keck, and the bottom ones are for JWST NIRCam. And I found this sort of like nice limit that where it looked like it should be theoretically possible from this set of models to find planets down to the size of Neptune if the system is younger than 1 gigayear and the targets are within 6 parsecs of us. So then the question became, are there some targets like this? And I was able to find 6 low mass M stars with this sort of perfect trifecta of youth, proximity, and contrast with the host star to form a small survey targeting these predicted ice giants from the direct imaging perspective. And this table shows the list of targets in what became the Cool Kids on the Block program. They are all expected to be less than 1 gig year of age. And since they're all M stars, the stars are not overwhelmingly bright. So it's easier to achieve the contrast that you need to get the planet. It's also great that we found 6 because it's typical to need sort of reference PSFs when you do this sort of work in direct imaging. And by finding 6, they could form a survey altogether where we wouldn't necessarily need dedicated reference stars. So it'd be more efficient. Okay, and here's where the game changes though. When you hunt for planets this cold, we run into some interesting issues if a planet is cloudy for its detectability. And here's a plot showing a custom model of a clear and cloudy exoplanet that's 75 Kelvin, so something sort of like Neptune temperature. And you can see that the MIRI 21 micron band shaded in gray on the right is strong for both clear and cloudy exoplanets. However, at the 4 micron bands, you only see sufficient flux if a planet is clear. And this means that the NIRCam only observations may miss certain planets completely. So to optimize, I'll also mention this plot. This is a plot of if you're taking the 2 bands that we're talking about. So this 4 micron band is in blue, this 21 is in red, and you can see how deeply some of these change in magnitude depending on if a planet is cloudy versus clear. This is can be over 10 magnitudes of difference at this temperature. And then the MIRI stays relatively the same. I highlight this because most JWST observing of exoplanets that went on in the first few cycles for JWST all used these NIRCam bands. So this is one of the only surveys that can pick up these really cold planets that are cloudy. So to optimize for all the possibilities, we decided to go with this dual band strategy where we used both NIRCam coronagraphic imaging and MIRI non-coronagraphic imaging at 21 microns. And so we got sort of a first look at what these 2 instruments can do. And yeah, we're helping sort of establish these first occurrence rates agnostic of the atmosphere of these planets. Okay, so the data came in. The data came in 2 rounds, one last December and another in April. And here's an example of one of our sets of images. And this is for Wolf 359, but now with JWST. NIRCam image is in blue, the MIRI image is in red, and this is what they all look like before we start the post-processing. They basically look like big splotchy snowflakes. That's the star. And then we remove the starlight using our post-processing techniques to reveal some faint sources underneath. And once we identify a source, we then check to see if a source is extended like a galaxy or if it's a point source like a planet. And so for those of you with a really good eye, you might be able to spot 2 faint candidates in the bottom MIRI image. The top NIRCam data doesn't have those sources, but again, that could be consistent with what we expect for a cold, cloudy planet. And I'll talk about if how we find if those sources are real in a second. But I want to just like quickly emphasize and drill the point home. We published some of our like first results of the comparison of these two imaging modes in a paper called NearCam Yells at Cloud. Logan Pierce also made a meme that goes with it over Old Man Yells at Cloud. And so although we can't identify yet with just that one first image if these sources are planets or background, we can check to see if the observations were doing what we thought they would. And lo and behold, we're getting great sensitivity. Here's one of our the contrast curves from 2 stars, and we're just showing here that we are seeing sort of like we can get into these ranges that we were hoping to get in of these solar system temperature planets. For clear, we do well with both NearCam and MIRI, but there's this big discrepancy. If you have a very cloudy planet, you can see much, much deeper with MIRI. So here's the same contrast curves, but converted into some absolute magnitudes and separation in AU. We're getting really good sensitivity to these planets that are colder than Jupiter for our very nearest target, and for our further targets, we're getting for all our targets, we're getting sort of in this Saturn to Jupiter temperature range using the MIRI non-coronagraphy bands. Okay, so I want to go back to that MIRI image and talk about how we can go about vetting these candidates for if they're background sources or if they're co-moving planets, and how we've been thinking about this strategy. So we had this great data set in December 2024 that showed showed 2 images here, or sorry, 2 candidates here. One of them is consistent with this 110K sub-Saturn at 10 AU. One is about the same temperature, a little further away. Also in this image, you may have noted, oh yeah, we also have sort of like 2 faint things that you can tell are extended galaxies in the background. There's also a couple of other things you might notice. One is this center here is an issue that we're having with the PSF subtraction due to a detector effect called the brighter fatter effect. It has to do with the PSFs becoming different shapes even if like pixels aren't saturated. And so our like self-referencing strategy with the survey is actually really tricky to pull off with MIRI, and we had not appreciated that before these observations came in. The other thing you might notice is this big blotch here. This is an image artifact, which actually let us request a redo of this image, since it's affecting a pretty big portion and there could be some secret planets under there. We asked Space Telescope for a redo of this image. And so that actually gives us the information that we need to do a check. So these candidates can get vetted by a proper motion check. And you can think of this strategy a lot like being a person riding on the train and trying to figure out who's on the train with you and who might be out the window. So if you are if you're a star riding a train and you're trying to figure out if the planet is on a train with you, you can take 2 pictures on the train. In both, if they're not if a source is not moving, you know it's a companion on the train with you. But if something is changing, you know it's out the window in the background. So let's see if we can do this with our 2 Wolf 359 images together. Let's go ahead and run this check. So here's the first images with the 2 candidates circled. And I'll now flip to the second image and we'll watch to see if those circled sources are moving with the star or if they're background galaxies. So the star will stay centered, so the candidates shouldn't move if there are any planets. So here's image 1, image 2, first, second, first, second, sadness. So in this particular case, we saw these sources moving with the background galaxies. This scenario really highlights the importance of completing this sort of proper motion follow-up observations, especially when we're using JWST MIRI, which is so sensitive to classes of objects we've never seen before. As a background source, that particular source is also of interest. Average galaxies aren't necessarily that near-cam dark and have a ratio that's closer to 10 between these two bands, between the like near-cam and MIRI bands. So this source is at least 25 times brighter in MIRI. I don't know what it is. I found that it's a bit of a Rorschach test for whenever people are working on, like whatever people are working on, you ask around, if you're like, hey, brown dwarf observers, what's that? They say, it's a brown dwarf. If you work on near-cam dark objects, feel free to come find me. I think some of the galaxy folks are starting to feel like maybe it's more run-of-the-mill, getting a sense from them. So, but yeah, if you're interested in that, please feel free to come bug me. Okay, in every system we imaged, we have at least one candidate. And that could be feasible. So it's something that looks about right in terms of brightness and is passing the initial like point source fitting tests. I pointed them out with a green arrow here to just show you a sense, and I've labeled some, but not all of them, with their measured temperatures and orbit separation and mass estimate. We're getting a lot of feasible candidates between 100 and 200 Kelvin, or that could be the equivalent of planets that are between 100 and 200 Kelvin and are around 0.1 Jupiter masses, all within 100 AU. But these could also easily be background objects as well. And to understand if these are planets, we just need data with a second time epoch to do that proper motion check. But if they are real, there are a couple of interesting things this starts to open. And I want to just like take a brief aside to talk about some of the other things we've been thinking about with these very nearby systems. So in the event that these are real, it turns out that visible and short wavelength IR light can be very reflective off of icy rings. And so even if you might be able to create this horrible scenario where you suppress the near-cam flux in F444 with water clouds and have a big giant icy ring at F200, so a shorter wavelength band. And you might be able to get a detection of a very large exoring system around these planets using the near-cam data. And I wrote a paper last year showing that like it is possible that near-cam could serendipitously detect large ring systems that are sort of between this like 3 times the size of Saturn's rings at the smallest and the size of like what you might think of like a circumplanetary disk. I think there's a lot to explore here. I don't think JWST is going to be the best instrument for this. I think there's a real chance that maybe some ground-based instruments could do some weird stuff with this. And I think there's a real chance that Roman CGI might make a good test bed that will automatically be getting a lot of visible light reflected imaging. And it might just accidentally pick up a whole bunch of like icy disks, because icy disks are really, icy rings are really reflective. Icy rings / protoplanetary disks. These systems are also really good candidates for trying to search for moons. We had an undergraduate work with us last summer named Matson Garza, who did a project where he took the EPS-INDI AB detection. So there's that beautiful detection from Elizabeth Matthews that I mentioned, where you see that the planet looks as bright as like some stars. And rather than making a contrast curve of the star, he made a contrast curve of the planet and tried to rule out this as a binary planet like system or like put some upper limits on like how big a moon could be around Epsilon Indi AB. Little weird, but like is totally actually starting to become feasibly possible with JWST. So in addition to the systems that I just talked about, I also have a Cycle 4 program running right now called Hot on the Hunt for frigid exoplanets in the solar system, solar neighborhood, which it definitely totally abbreviates to HOTH. And you can blame Andrew Vandenberg for that acronym. The program is a survey program, so it means that it's a gap filler program for the space telescopes where you can submit a bunch of targets, and when they're not observing other things and they just need an observation to fill in, they grab something from the list and then they like throw it up on the telescope and you get some data. So we gave them a list of 125 stars from about the 150-ish neighboring systems, where we can get these really good sensitivities to cold planets. So using sort of the results we saw from Cool Kids on the Block, we said, where can we see planets that are colder than Jupiter? And then we repeated a similar observation mode and then gave them a giant list. So this program opens up this sorts of MIRI imaging observation to FGK stars, as well as older M systems, as well as binaries and some triple systems. We will get 3 colors of MIRI non-coronagraphic imaging at MIRI's longest wavelengths. So that's 18 microns, 21 microns, and 25.5 microns. And this is to optimize the chances of finding these most frigid planets we can. The coldest planet that we could theoretically see in this survey is about 55K if we got data on the nearest star in the sample, which is Proxima Centauri. And yeah, again, we have sensitivity for planets colder than Jupiter and the rest. So we've had 2 observations so far. And we found a companion, except that I found it in archival data while looking for some reference stuff. So part of the challenge with our survey program is we don't have any dedicated reference images. I went to the archival image catalog and started looking to see what images might make nice PSF references. And lo and behold, while searching through the archival data, we totally got our first detection from the survey, yeah. But what was actually going on is I pulled up a calibrator star and I noticed it had this weird lump right here. I don't know if you can see that. And so I ran it through the Cool Kids on the Block / Hoth pipeline and a companion popped out. So it's a nice example of sort of what we theoretically could be able to achieve with this sort of data. It's a little over 1 arcsecond in separation at about 11 pixels. So like just outside sort of that like lambda over D region. Look like you have a question.
Yeah. Sorry, when you say calibrator star, do you mean it was a
it's a photometric calibrator, yeah.
From a calibration program.
From a calibration program.
Amazing.
So I emailed Space Telescope and was like, hello, do you know your calibrator has binary? Here it is. And
Beta door by any chance?
what's that?
Beta door by any chance?
It is not beta door. It is HD101 something. I can't remember its telephone digit, but the Michigan postdocs started to call it Lumpford. So it's now gotten the nickname Lumpford, the calibrator star, because it's got a nice little lump.
Yeah, there have been mistakes.
What's its contrast? Or maybe you'll get.
I figured this out like last week, so I haven't actually done the full analysis on it. I'm guessing it's probably an M star. The calibrator star was an A star, and it was so bright that we could see it by eye, and it's not super nearby. So I assume it's a stellar companion. Okay. But jokes aside of me finding companions in archival data using this sort of method, we've had two stars from the survey observed so far. And one of them was a M-dwarf binary system. And if you color stack the three colors, there's something that's like a really, really low signal to noise candidate that's starting to pop out that's sort of like at 7.5 AU and would be between the temperature of Saturn and Jupiter. The system doesn't have great age dating, so I can't tell you exactly what the mass of something like that would be. But I think what this is maybe showing, and again, I'm not totally sure if this is a real candidate yet, or if this is something to do with the way I was doing the PSF subtraction. But it's a nice early sign that this sort of program and this sort of like strategies with MIRI non-coronagraphic imaging could really yield both candidates that are far away from their stars, that are galaxy confused, but also closer to this sort of like speckled limited regime in that sort of like 1 to 10 AU goal area. So yeah, freezing off the press, a candidate around an M-star binary. And I have lots of other ideas that I want to explore this year, and I'd love to grow my collaborations. I've recently been wondering if a lot of this data set could get used to do interesting disk constraints. And this is an area of science that like clearly for cycle 5, there was like 25.5 micron disk imaging program that went in that's going to get imaging of a bunch of sun-like stars. And like we're getting this imaging just sort of for free in this program. Less sensitive than the dedicated cycle 5 program will get, but like there's got to be something we can do with disks, right? I don't know. The other thing that I've been exploring is this data and the way that we're taking these non-coronagraphic imaging with JWST looks a heck of a lot like what you do when you take the DDT transit rocky worlds data, where we're getting this, we're not switching it to time series mode. So it's like a little different, but like with a little bit of massaging, I think we can pull out light curves of the star, and we might be able to pull out light curves of background objects too. And I don't know where this is going yet, but we did make a connection with a group in New Zealand who's been writing a pipeline to do just this, but for the transient science case, but hasn't tried to apply it to planetary science at all yet. So I've been wondering if maybe some of this data could be valuable for either getting light curves of the star, or in the case of like going back to maybe like some of these detected planets with JWST, breaking the images up into more time series components and then trying to do some sort of time domain astronomy with it. Yeah.
If any of your objects have MIPS 24 micron axis?
I haven't checked. Yeah. Yeah.
Give a precursor.
Yep. So yeah, tons to explore here. And then I also just really like thinking about, because we're starting to push into this regime where we're really actually starting to probe for these cold planets that are more like our own solar system giant planets. What other like things have we learned from solar system science going back to the 70s that we can now like just start to do with exoplanets, because we're starting to get some of this interesting imaging. So yeah, if you like thinking about exoplanets and solar system connections, I've also been trying to grow some of this work into that area. Yeah, so with that, I'll leave my summary up and open the floor for any other discussions and questions. Yeah.
So 2 questions. So one, do you have a bunch more A stars in the calibrator sample? Because I'm not sure if you're aware,
Yes.
right? This is a really hard to probe separation and mass ratio range for A stars, right? They're terrible for RBs. So, right, this is like, we've done a really good job surveying binary parameter space, but not this region, I think. I don't remember the exact separation ranges, but you might be able to fill in a really key sweet spot in companion frequency that we don't have.
That's wonderful. I had not actually thought about trying to do anything with scientifically with the other A-star calibrators, but like it's really easy to pull out this sort of data for them. One of the beautiful things that I also didn't mention in this main talk that with these super nearby stars, so with Hoth and with Cool Kids on the Block, the stars are so bright in 21 microns that we suffer from the brighter fatter effect, but we don't seem to suffer in 25 microns as much. And we don't seem to suffer with these calibrator stars either. They're just dim enough that it seems like they're dipping under the brightness where it's like really an issue. So we're able, like, this is really truly like you can see there's no brighter fatter in that center. And maybe the signal is so booming that it drowns out any that's there, but we're just able to get a really nice, clean PSF subtraction of the archival images of the calibrator stars.
I mean, if nobody's run this kind of check, I mean, in principle, there could be a pretty high occurrence rate in that region. I did like just do a few other ones as I was like looking through, and nothing had as obvious of a lump as this particular one that I'm showing, but I also haven't dug through the full MAST archive yet. Yeah, I mean, or, you know, next time around, throw some A-stars into your FGK bins for the survey overall. I think it's probably not that many that are super nearby, but but I had one other follow-up question, which is what is the expected background contamination rate in either of your surveys?
Yeah, I don't have the numbers off the top of my head.
Is it this or much lower? Because I mean.
Yeah, I haven't run that specific. The cycle 3 time, I'm not sure we knew the answer to that, but we might be getting a better handle on it now that there's more MIRI data. And I know it can depend. I haven't done a careful analysis of it. I should just say that.
So is there any then meaning the actual model, the prediction of number of galaxies you expect in here from the JWST other data?
Yeah.
And then the one contamination by the extragalactic sources, one you can use a galactic model to predict how many you can expect in that field of view.
Yeah.
Galactic.
Yeah, I think it'd be pretty hard to gain enough prediction that you're like, yeah, we're definitely seeing more than we should. Like I think the error bars for that sort of prediction is too high.
Even for the brown dwarf M-dwarfs? I mean, I'd be surprised, but I mean, for the galaxies, I get there's uncertainty, then but those are easier to tell.
Yeah.
It's the brown dwarfs and the M-dwarfs that I would guess would be.
I don't think we haven't too much of I'm not sure. I should just say I'm not sure.
Galaxies, I mean, there were statistical studies for Spitzer. Back in case of problem, which has a good paper on background galaxy contamination of these wavelengths.
Yeah.
I think that could be extrapolated down to.
Yeah, I know Michael Meyer's group has been putting a lot of effort towards this sort of work as well.
Right, especially for the brown dwarf and that mass regime, you may be. I think there should be some good number.
Matthew DeFerrio's thesis.
Yeah,
right.
Yeah, Matthew DeFerio did his PhD with Michael Meyer.
Yeah, well,
yeah.
Fuda, do you want to ask your question?
Yeah, hi Rachel, great talk. Fuda from Planetary Science. I have a question about the exo rings. Do you know if there'd be like a good inclination angles where the reflection from these exo rings would be like the most appropriate?
We've been sort of treating it so I don't know the answer to that if there's particular favorite systems. I do know that JWST has already taken this for our own solar system, if that's of interest. That's what I have up on the screen right now. In my paper, when I did the sort of what could we see with JWST, I assume the best possible scenarios that you could get. So I assumed like a 100% reflection and a more like Saturn-like reflection, and that we are getting all of the light from the ring that we possibly could. So I just have ignored geometry so far, just out of a curiosity more if it's a possibility. I know that there are some groups that are looking more into this for the Roman CGI case and are thinking more about the geometry, but I'm less familiar with the details of it.
other questions? Any questions from the online audience?
I have one. We can request reserve. What are your plans as a second fellow besides these two programs?
Yeah, gosh, there's so much work to finish up on Hoth and the Cool Kids on the Block project for sure. So that was one of the projects I pitched, was just like trying to finish up what's going on here. Another thing that I've sort of been thinking about, I mentioned going from my data into light curves. You can also take light curve time series data and turn it into a direct imaging analysis. And a lot of the machinery that we set up for Cool Kids on the Block and for Hoth can also work for the DDT transit observation time series programs. So I've been thinking about that, although I suspect actually that other people are thinking about that too, and that there are going to be some students who maybe hop on some of those analysis projects where you take the TRAPPIST system and you turn it into a direct imaging analysis, because it's like a 10-hour MIRI imaging data set, and you can get extremely deep like direct imaging limits from that. And then yeah, I've been curious about this sort of like rings and moons case, if there's more that we can develop there before HWO is suddenly contaminated by a bunch of rings. Yeah.
Also on the topic of rings, do you think about polarimetry with ALMA and whether that would help?
You know, I've been curious about
analogy to like PDS.
Yeah, I've been curious about the polarimetry case. I was asking Briley Lewis some questions about it too, but we didn't develop it very far. So it's something I've still been curious about. I wasn't thinking about it from ALMA. I was thinking about it from wondering if GPI2 would maybe do something interesting, because I know that they're also supposed to have polarimetry with GPI. So yeah, I think there's a door. I think there's a door there. I'm not sure if it's a good door.
We don't have other questions. Let's thank our speaker again. And Rachel will stay with us today and tomorrow, I think.
Yes.
And if you have any questions, you can just keep discussing, and the sign-up sheet is sent out together with the email for the Origin seminar, and you can sign up there. Thank you.
Okay, so